Welcome to the first lecture of this video course, and this lecture is 1.1 and it is introducing the MATLAB platform. So this is the broad outline of this lecture. So we'll talk about what in the real world is required to be captured by a model. Then we'll discuss about the simulations and its tools which are required to analyze the real world. And finally, we will get into some of the platforms that are available for doing simulations. So let us see what the real world looks like. The real world objects are not easily accessible to a person doing an experiment. The reasons for these is mainly due to the cost constraints, because if you want to analyze a real system, the measurements requires very costly equipments to directly deal with the real world. Secondly, on doing an experiment in the real world can cause unintentional changes due to some glitches that we perform during the experiment. And thirdly, the real world suffers from uncertainty. Suppose you want to measure a quantity. Due to the duality of nature, it is not possible to do two simultaneous measurements at the same time. Since it is essential to work on the real world, we need to abstract the essential informations of the nature through a process known as modeling to get a full understanding about the situation or the real world situation. We illustrate this with the example shown here. So this situation is a wireless channel where an antenna radiates energy, electromagnetic waves, and we want to study what effect the wireless channel or the wireless environment has on this transmitted EM waves. Now, as mentioned earlier, we require highly sophisticated measuring devices to perform this task. Now, suppose a person can afford to buy such an equipment also. How real or how good can he perform this task is a question that needs to be analyzed. So instead of going and measuring the channel directly, one will abstract the essential information, or one will try to model the situation with the help of some mathematical models and then work with the model. For instance, in the wireless channel, the environment is composed of three different types of attenuations. One is called as the fading, the second is shadowing, and the third is path losses. So these three kinds of attenuations has a random element, especially the first two has got a random component along with it, which can model the wireless channel somewhat or to a decent extent. Now, what is abstraction? So, we have an object in the real world and we extract the essential information that we require to work with the real world into a model. Now, the listener can ask this question: are all models good? The answer is no. Some models are good, but model obtained through abstraction is definitely a useful tool in understanding the real world, which otherwise would have been made would have been difficult to perform. We provide two examples to understand this. Consider a metal. A metal is a very good conductor. So what we do in the abstract model is that we represent a metallic object by a wire, which is represented or denoted by the straight line. Now what it denotes, or what our model denotes, is that whatever current that passes through a metallic object is non-dissipated, or you get complete conduction within that wire. On the other hand, a non-metallic object can be modeled by a resistor, which is represented symbolically by the zigzag lines. So what it represents is that when you pass a current, the object offers some resistance to the flow of current, which appears as the voltage across the. Now we'll see what makes the modeling possible. So in most of the engineering practices, we see people work on models and they work on simulations with these models. So let us see an input-output relationship between the real world and the model. So we apply the same input, which is represented in the green box, to the real world as well as the model. And we receive some output represented in the violet box from the real world, whereas something that is in the blue box in the model. Now, we need to find out how good the model works. So if the model works quite good, if I take some measure of the error between the outputs, it should be minimized. In some cases, I will be interested in a square error. Some cases, shall be interested in the absolute error. And in some other cases, you will look into some other measure of errors. But in short, we are looking for some error between the two outputs. So depending on how small the error is, the model can be accepted or it can be declined. We show an example of a voltage regulator and how it is possible to model this functionality using one of the simulators that we are going to see. So what is the functioning of a voltage regulator? We have an input voltage coming in the range of 180 to 240 volts. And the regulator system should regulate the voltage to a range of 200 to 220 volts. This can be simplified and written in the form of an algorithm. So the regulator system is nothing but, if an input in the range 180 to 200 comes into the regulator system, it should boost up that voltage to 200. So that is the first condition of the regulator system. Now, if a voltage comes in the range 220 to 240, then a step down of the voltage is required to 220 volts. In every other situation, I can write or I can send V out equal to V in. Whatever input comes to the output. So that is the small algorithmic model that we have designed for the regulator system. Now one can easily write a short code and see the functionality of the system through the abstraction that we have enabled here. Finally, we get down to some of the platforms that are available to perform this simulation or to perform the modeling and to see how the real world can be modeled using one of the tools. Now, in this slide, MATLAB is a purchased version, or it's a non-free version. The remaining three are open source and freely available. So I highly recommend you to try one of these as we do this course. So that is the end of this lecture. Thank you.